Okay, in this presentation we're going to look at joint random variables. So the joint probability mass function of x and y is tabulated as follows. So we have it there, x is equal to -1, 0 and 1, or 1, and y is equal to 0, 1 or 2. And those are the joint probabilities of each. So essentially what we're going to do there in a short moment is tot them all up and check that they add up to 1. Of course they do, but we should always check that. So obtain the marginal distributions of x and y and calculate the expected value of x, the expected value of y, the variance of x, and the variance of y. So let's scroll down here. The marginal distributions of x and y are shown and appended to the table. So essentially what we do is add up the rows and row totals and column totals of each of the probabilities. Just a quick example there, 1/6 plus 1/12 plus 1/12. Add that up, we would get, let's say, 4/12, which is 1/3. And likewise, the whole way through. We do that for the column totals as well. And we should check that they all add up to 1. Okay, now, in this case, it's sort of almost self-explanatory, but you can always do it by inspection there, but it's always worth checking. Now, the both variables are equally spaced out between the middle value, 0, 1 and 2, -1 and 0. And they're all equally likely. So in this case, you could almost tell by inspection that the expected value of x is going to be equal to 0 and y is equal to 1. Now you can work it out by explicit calculation, but in this case it should be fairly straightforward just to state it. Because what we're going to do here is a longer question. Okay, now this is a case that the expected values are fairly simple. In other questions it would take a proper calculation. So essentially what we're going to do here is sum up the values and the values subtracting the mean in each case. Here it's x minus 0 and in this other case it's y minus 1. Square that and multiply by the probabilities. Now in this case it's should be a fairly quick calculation here. The mean of x is 0, so we subtract 0 from each of the three possible values, -1, 0 and 1. We square that and we also multiply by the probability. Here that's equivalent to dividing it by 3. -1 minus 0 squared divided by 3, that's 1/3. 0 minus 0 squared over 3, 0. 1 minus 0 squared over 3, that's 1/3 plus 0 plus 1/3, 2/3. Likewise, we get a similar sort of answer down here. Okay, so in this case the variance of both x and y is 2/3, 2/3. Now, because x and y are linearly related, y is equal to x plus 1, okay, that we can say that the variance of x must be necessarily the variance of y. If you spot that relationship, you can use that, justify it on that basis. Moving on to part B, obtain the conditional distribution of y for each possible value of x, and hence show that the expected value of y for each value of x, given each value of x, the conditional expectation is a linear function of x. Okay, so what I'm going to do here, first off, is concentrate on, let's say, x equal to -1, and let's just focus in on that part only. Now, I actually have put in the values there, but I'll just explain where they come from. So previously we found that the column, that row total from the previous table was 1/3. In fact, let's just go back and have a look at that there. There it is there. There we go. So what we have to do is essentially multiply it such that the total should add up to 1. So all we have to do is multiply each of the three values by 3, such that 1/3 will go to 1. So essentially what we have to do here is 1/6, multiply that by 3, we get 1/2. 1/12, multiply that by 3, we get 1/4, and likewise 1/4 here. And we do that the whole way through because we actually are multiplying by 3 in each of the instance, going from 1/3 to 1. Essentially we just triple every single probability there. Now, these are conditional distributions of y for each value of x. So the total thing does not have to add up to 1. It's essentially what does have to happen is that this row here has to total 1, this row here has to total 1, and this row here has to total 1. Okay, so essentially all you have to do is make that happen by multiplying it accordingly. Now, again, you also we're working on the basis of y for each possible value of x. So we're working by the rows here. If it was the other way around, we'd be looking at the columns. The conditional distribution of x for each possible value of y. In that case, what we would be doing is working down the rows. So let's just get rid of that. Essentially, what we'd have to do there is you could demonstrate it or rationalize a little bit more like how I've just done there. But essentially, that is the answer there. Now, so moving on to the next part, what we're going to look at is the conditional expectations or the conditional means of y given each of the three values of x, -1, 0, and 1. Okay, so what we're going to do here is in each of the three calculations, what we have is a value of y, 0, 1, and 2. Okay, and what we're going to do is multiply them by the corresponding probabilities, the corresponding conditional probabilities from the table above. So let's just move that back to the table above. So here are our values of y, 0, 1, and 2. And these are the conditional probabilities for the first calculation, which is a half, a quarter, and a quarter. Or down here I have it as 0.25, 0.5, 0.25, and 0.25. So this is a discrete random variable calculation. Value times the probability of that value, add them all up. 0 times 0.5 gives us 0. 1 times 0.25, 0.25. 2 times 0.25, that is 0.75. And the other calculations work the same way. For example, x equal to 0. What we have there is a quarter, a half, and a quarter. Let's just sort of keep that in shot there so that we can see it all together. There we have those there. And my values of y are above, 0, 1, and 2 again. Okay. So I think actually I'm making my point clear enough. So 0, 1, and 2, the probabilities are 0.25, 0.5, and 0.25. When we tot them up, multiply them out and tot them up, we get 1. And finally, likewise for x equal to 1, what is the conditional mean of that? Working it out the same way again, we would get a value of 1.25, which is 5 over 4. Now, that's straightforward enough. The next part is, is there a linear relationship between the conditional means and the underlying values of x? So let's just check that. So here we have -1, 0, and 1. And the conditional means are 0.75, 1.00, and 1.25. Okay, now there's a unit increase of going from each consecutive value of x. So we go from -1 to 0, that's an increase of +1. And 0 to 1, that's a unit increase of +1 as well. Okay, so there's a consistent increase over here. Do we see that on the opposite side? Well, we have 0.75 to 1. That is a unit increase of 0.25. Okay, and 1 to 1.25, again, we see a unit increase of 0.5. So we get consistent unit increases on both sides. +1 and 0.25. So that's strong evidence. That proves a linear relationship between the two. So for each unit of x, the conditional mean goes up by 0.25. So the slope is 0.25. So the linear relationship can be expressed as follows. I'll just write that out a bit bigger. X over 4, x is the underlying variable, a quarter, or 0.25 is the slope. And afterwards, you would work out that the constant should be equal to 1 just to make the numbers work. So that is the part B there. Find the expected value of x times y and deduce the covariance of x and y and the correlation of x and y. Are x and y independent? So here's the table again. That's the original table. And essentially what we're going to do is multiply each possible value of x and y, each possible combination, and also multiply by the probability. It's a bit of number crunching, but it should work out fairly quickly. Essentially, y equal to 0. I have it sort of structured here so that each cell corresponds, each of these calculations is located corresponding to a cell. Essentially what's going to happen here is the multiples of x and y will be 0 in these rows and columns. Okay, so that's 0 there, 0 there, 0 there, that goes to 0, and that one goes to 0. So essentially what we're left is this one here, this cell here, this cell here, and this cell here. Now you can actually just put in 0 there for the other ones, because you could just sort of automatically state where we're multiplying by 0, we just leave a 0. So what we're left with, I've just done it in the long form there, minus 1 times 1 times 1/12, that gives us minus 1 over 12. Minus 1 times 2 times 1/12 is minus 2 over 12. Let's just double check that with our table. Minus 1 times 1 times 1/12, that gives us minus 12, minus 1 over 12. And minus 1 to 1/12, that gives us minus 2 over 12. And likewise down here, 1 times 1 over 12, that gives us 1 over 12. And then finally 2/6. So some of these numbers cancel out again. For example, that and that cancel each other out. Minus 2 over 12 is minus 1/6. That's 2/6. So essentially what we end up with is, just let's move down here, we end up with expected value of the product of x and y equal to 1/6. Now, the covariance, this is a formula you should know off by heart. This will come up quite a lot in these type of questions. It's very similar to the variance formula. The covariance of x and y is the expected value of the product of x and y times the expected value of x times the expected value of y. So here we have 1/6, which is what we just calculated up here. And previously we found that the expected value of x is 0, the expected value of y is 1. Essentially that's just going to cancel out to 0. So what we're left with is 1/6. Moving on, we're asked to find the correlation of x and y, and that is simply calculated using the covariance of x and y and the variances of x and y. So we have the covariance of x and y and the square root of the product of the variances of x and y. So variance of x times the variance of y, get the square root of that. Okay, so we have 1/6, which we found in the last part, that's our covariance, and divided by the square root of 2/3, which is the variance of x, times 2/3, which is the variance of y. That works out to be simply 2/3. That simplifies very quickly to just 2/3. So we have 1/6 divided by 2/3. Working that out algebraically, that should be 1/4, 1 over 4. So x and y are not independent, which is the last part of this question. Their correlation and their covariance is non-zero, and in fact earlier on we found that they are linearly related. The last part of this video is asking us to find the probability of the distribution of z, or z, which is equal to x cubed plus y minus 1 to be cubed. So essentially what we have to do here is essentially just multiply them out. I'm going to do this in very short steps here. So we have minus 1 cubed is minus 1. 0 is 0. So when we have 0 minus 1 and cube that, we also have minus 1. So minus 1 times minus 1 gives us minus 2. And so on for the rest of them. We have minus 1 there, 0, 1, and so on. You get the idea. So the possible values are, we have a minus 2, a minus 1, a 0, there's a minus 1 again, another 0, 1, 0 again, 1, and 2. Okay, so let's just box them up, or sort of combine them. So we have minus 2 here. Okay. We have minus 1s here. So I'm just going to... They sort of work along the diagonals, essentially, is what I'm getting at. We have the zeros here. The ones here. And finally 2 here. Okay, so essentially what we have to do is just combine that, inspect that table, add them all up. For example, the zeros, which are along the diagonal, this diagonal here, 1/12 plus 1/6 plus 1/12, that gives us 1/3. Okay, so it seems that if we tot them all up, that each of the 5 possible outcomes of z, which we have to figure out, minus 2, minus 1, 0, 1, and 2, they're all equally... No, sorry, they're not all equally likely. They are all equally likely apart from 0, which is 1/3. Okay, so that is either 1/6 or 1/3. Okay, so that is it. Now, this question doesn't ask us to do anything more. It leaves it there. But other questions we probably would be expected to do a little bit more with that. So we'll wrap it up there, and thank you very much.